Thanks for joining. We're about to do some practice problems, which is one of the best ways that we have to help us learn. Now, if you haven't tried these problems yourself, please try them yourself first. There's this beautiful button. It's somewhere along here called pause. Make use of it. See the problem? Pause. Try it yourself. Then if you need to, you can unpause and we can compare answers. In this way, you get engaged, you'll learn, you'll succeed. And that's what we want, your success. Let's get going. Number 1. We need to find the Laplace transform of 15 minus 12 to the 5 halves minus 10 e to the minus 4t cosine squared 3t. Well, before we begin, we say, okay, we have linearity, so we should check, are we happy with each piece? 15, great. Constant, Bob's your uncle, life is good. T to a power, we can handle that. We have ways. And now, this last part, exponential, we love exponentials. Laplace transform loves exponentials. Cosine squared of 3t. Ooh, now a cosine 3t, we're happy with. But cosine squared, not so much. It's not on our list. And now you're saying, what list? Well, we have our formula sheet. And this is going to become our, bread and butter. We're going to keep coming back over and over. And you notice we can do cosine and sine, but we don't have cosine squared or sine squared. Okay, so we have a problem. But with every problem comes an opportunity. What's our opportunity here? We say, can we rewrite it? Think about it a lot like what you would do in integration. How can I rewrite this so it matches with things I can do? So when it comes to trig, the only things you can really do involve sines and cosines. So if it's not a straight up sine or a straight up cosine, maybe some other pieces attached, but we'll get to those later. Then we need to do some work. So we say, all right, let's think about cosine squared 3t. What can we do to rewrite this using things that'll make us happy? In other words, get rid of the square. Well, we come back to our formula sheet and we say, wouldn't you know there's a lot of trig stuff over here. And one of the trig things involves a square. Cosine squared is power reduction. Half times 1 plus cosine 2t. So what we can do is we can replace this. This cosine squared becomes a 1/2 1 plus cosine of 6t. All right, so if we do that change, what do we really have? This becomes the Laplace of the first two things we said we were happy with, so we're not going to change those. And then we have 10 times a half makes a 5. And so we have 5 e to the minus 4t, so minus e to the minus 4t times the 5. Don't forget the 5. Ha ha ha, even after I just said it. And then, of course, 10 and a half, again 5, and again there's a minus. Minus 5, and don't forget the e to the minus 4t again. Cosine 6t. All right, so there we go. Now we're ready. All right, well, we use linearity. And linearity says we can think of this as, instead of one big thing, 4 little things. So we have 15 times the Laplace of 1 minus 12 times the Laplace t to the 5 halves minus 5 Laplace e to the minus 4t and minus 5 Laplace e to the minus 4t cosine 6t. All right, well, let's go through and talk about these one at a time. So we'll start with the Laplace of 1. Do we know what it is? Well, yeah, it's actually on our table. Laplace of 1, 1 over s. We say, okay, so this part is 1 over s. All right, how about the Laplace of t to the 5 halves? Now for that, that's t to a power, so that's t to a power there. Now it says Laplace of t to the beta is this function called gamma beta plus 1 over s to the beta plus 1. So if we just write this down, beta is 5 halves. So just this part right here would say we want gamma 5 halves plus 1 over s to the 5 halves plus 1, which would be 7 halves. We'll follow up more with that in a few moments. All right, e to the minus 4t, well, is that on there? Yeah. See, e to a power t. So e to something t, 1 over s minus. So minus 4t, so that's become 1 over s minus 4, s plus 4. All right, so that takes care of that term. And our last term. Now, our last term isn't explicitly on our sheet because, well, we couldn't fit everything, but really is a combination of two ideas. Namely, we know how to do the Laplace of just cosine. And then it says, oh, if you multiply by an exponential, shift. So, here's the idea. We say, look, we can do just the cosine by itself. So here's just the cosine. By itself, this would become s over s squared plus 36. Now this says what? It says do a shift. S goes to s minus 4, s plus 4. So we're going to take the Laplace of the cosine 60 and apply the shift, meaning what comes out? S plus 4 over s plus 4 squared plus 36. All right, 36, 6 squared. All right, so that's the last piece. Now, well, we have this gamma 5 halves plus 1. What can we do? Let's push a little bit further, because they like halves. Now, there's a nice pair of facts, and I want to point out, I'm not just going to write these down. They're on the formula sheet. Gamma of beta plus 1 is beta gamma beta, and gamma of a half is square root of pi. So let me write those down. So gamma beta plus 1, that's beta, gamma beta, and then gamma 1/2 is square root of pi. So let's start here. What do we have? We have gamma 5 halves plus 1. So according to this is beta is 5 halves, 5 halves, gamma 5 halves. Well, wait, 5 halves, that's the same as 3 halves plus 1. So what can we do? Well, this will become 5 halves times 3 halves times gamma of 3 halves. Well, wait a second. 3 halves is what? 3 halves is a half plus 1. So 5 halves times 3 halves times gamma of a half plus 1. And, okay, so what is this? 5 halves times 3 halves times 1/2 times gamma of a half, right? We're using the gamma. Beta plus 1 is beta gamma beta. So, well, wait, hold on. Gamma of a half, that's negative a half plus 1. No, we're not doing that. What are we doing? You see gamma of a half. That's square root of pi. So that's 5 halves times 3 halves times 1/2 times square root of pi. Or, if you like, 15 divided by 8 square root pi. All right, so what do we now have? Let's see if we can clean this up. We have 15 over s. That's our first term. Now here, what are we going to say? Well, this is 15 over 8 square root of pi. There's a 1 over s to the 7 halves. And then in front there's a 12. Now, 12 and 8 have a common factor of 4. So we can knock out a 4. So that would leave us with 2 here and 3 up here. So what do we have? We have minus 15 halves square root of pi, and I'll put 1 over s to the 7 halves. Minus 5 over s plus 4, then minus 5 times s plus 4 divided by s plus 4 quantity squared plus 36. And we're done. Nice, nice. Now you might be wondering, did we need to do that? I don't think the problem explicitly said it, but I think we should get into the habit of doing it, because sometimes they want us to make sure we can do things with the gamma function. Turns out it's a really nice function. It's kind of trying to be like, hey, what if we could make factorial work for all the numbers? And gamma's like, I can do that. And that turns out to have a lot of nice applications. So, all right, there we go. And I'm sure I'll say this many times, but make sure you learn how to distinguish your 5s from your s's. Even me, I'm starting to look at that and say, well, my 5s and my s's look very similar. So be careful. Be careful. All right, well, let's keep going. Oh, I forgot something. Well, let's fix it really quick. Easy fix. 3 times 15 is not 15. 3 times 15 is 45. Good, good. No one would have noticed, right? But, always make sure to get all the little bits and pieces. Because what do we want? All the points. Got to get them all. Number 2. Find the inverse Laplace, all right, because that's the minus 1 inverse Laplace, 2s minus 11 over s squared plus 4s plus 13. Let's start by looking at our denominator. S squared plus 4s plus 13. Does it factor in a nice way? And in other words, can you think of two numbers that multiply together to give 13, but you would add and you would get 4? No, I don't think there are such numbers. So what can we do? Well, what I'd recommend doing is, if you don't have a nice way to factor, ask yourself the question, can I complete the square? So let's try that. So we're going to take this s squared plus 4s plus 13. And we say, okay, start with s squared plus 4s. And now the question is, what should I add here so that this whole thing becomes something squared? That's the idea of complete the square. And we say, well, since we have a 1 in front, that's good news for us. Take the term in front of the s, divide by 2, which would give us 2. Square that. Says, well, if it was a 4, then life would be good. In fact, it would become s plus 2 quantity squared. Nice. Now, the problem is we don't have a plus 4. We have a plus 13. So we say, well, that leaves us with 9 left over. So we say, it's s plus 2 squared plus 9. All right. Now, what is this signaling? When you see something in your denominator, and you're taking inverse Laplace, and you see s plus or minus something squared plus another number, usually it's going to be a square, we say, oh, that's signaling sines and cosines. Because we see it's not just s, it's an s plus something, that's signaling we have a shift. So there's 3 rules we're going to want to lean into here. The sine, the cosine, and the shift. So those are the 3 rules that we're going to focus on. All right. And by the way, I'll say this many times, I hope, because it's important to hear. One of the challenges that you will have as you go forward is to learn to recognize, when do I use which formula? So you should think about it, right? Don't just take for granted like, it'll come to me in the moment. think about, why am I using this formula? Why am I not using that formula? How would I know to use this formula? So for us, the key thing was when we saw what we would call an irreducible quadratic downstairs. That signals something with sines and cosines. Because we saw a shift, that signals the shift formula. That's how we know which formulas to key off of. All right, so now let's come back to our expression. Almost all of our work is going to come down to understanding how do we write things, or more particularly, how do we rewrite them so that they're friendly with the table. So this is the inverse Laplace of downstairs s plus 2 squared, and I'll go ahead and write this as 3 squared. All right, and we'll do this in a few steps just so we can follow along. Now, what would we like to do upstairs? And this is important to understand. We say, well, downstairs, see how we have things expressed in terms of s plus 2? We want to mimic that upstairs. So in other words, if we see a shift happening downstairs and there's an upstairs term, we want that upstairs to have that same kind of shift. So we're like, okay, so plan. We're going to rewrite the top in terms of s plus 2. Okay, well, that's not too bad. How can you do that? Well, there's a fancy way, so I'm going to be very unfancy. And here's a fun trick. What's another way to say s? Another way to say s is s plus 2 minus 2. It's very true, right? S plus 2 minus 2 is s, so this is 2s minus 11. And so if you're having a hard time, this will always get you through because it doesn't require too much thought. Now we can distribute and update. We say, well, what does this become? Inverse Laplace, we have 2 times s plus 2, 2 minus 2, right, because we've got to distribute to both terms. 2 minus 2 is minus 4. Minus 11 is minus 15 over s plus 2 squared plus 3 squared. All right, good, good. We are doing wonderful. So, what's our next step? Well, now that we have this, we're going to split this into two parts. And for reference, let's write down our rules. We have that the Laplace of cosine of bt, well, that is, and I have to double check, so I pull my formula sheet, that's the one that has the s upstairs over s squared plus b squared. The Laplace of sine of bt, well, that would be the one that has the b over s squared plus b squared, and our shift formula, I'll write it down for reference, Laplace e to the bt f of t is f of s minus b. So, notice we have s plus 2. So, we say, oh, that says our shift is minus 2. So this part indicates b equals minus 2. That's our shift. And so what we can do is we can combine these two rules, and I'm going to write them down for reference, and I'm going to use explicitly a minus 2. And it says, if you take the Laplace of e to the minus 2t cosine bt, I'm not even going to specify what the b is, what is that going to become? Well, that says replace every s with s minus minus 2. So all the s's become s plus 2's. So s plus 2 over s plus 2 squared plus 3 squared. And the Laplace e to the minus 2t sine of bt, what will that be? Well, again, we take every s, replaced by s minus minus 2, s plus 2. So that becomes a b over s plus 2 squared plus 3 squared. And we say, ah, great. See, these are looking a lot like those. So we say, okay, let's break it into two parts. Use the power of linearity. But it was important that we first said, oh, we need to rewrite the numerator in terms of s plus 2 because we needed s plus 2's in the right places. So we'll have the following in the first term. We'll pull a 2 out. 2 inverse Laplace of s plus 2 over s plus 2 squared plus 3 squared. Now in the second term, what do we want to have? Well, we want to have, whoops, these should not be 3 squares. These should be b squared. Sorry about that. B, in this case, is 3. So we really want a 3 upstairs left. We had a 15. So we're going to pull out a 5. And so what's left is 3 over s plus 2 squared plus 3 squared. And now we're happy because these follow our formula. And we can say the following. The first one, well, that would correspond with e to the minus 2t cosine of 3t. And this one, e to the minus 2t sine of 3t. And so our final answer, 2 e to the minus 2t cosine of 3t minus 5 e to the minus 2t sine of 3t. And we are done. That's it. All right, good. Now, I know we're going slowly, and it's like, oh, there's a lot of steps. But once you get the hang of it, you're like, oh, that's not so bad. I can do this. And that's because you can do this. We believe in you. But it takes practice. It takes familiarity with what's in the table. Learn the table, and the table will help you to help get you all the points. Gotta get them all. All right, let's keep going. Number 3. Find the Laplace transform of, and there's this very long thing, 2u minus t squared plus 10t minus 21 minus 6u t minus t u 5 minus t. Okay, oh my goodness. What can we do? Well, what do we see? We're seeing on-off switches occurring. Remember, what is u? U is it's the unit step function, or I like to call it, the on-off switch. It's also called the Heaviside function. We say, okay, well, the problem is we have a nice rule for just u. And it's on our formula sheet. It's right here. The Laplace of u of t minus a is e to the minus as over s. So we'll just write that down for reference. The Laplace u t minus a is e to the minus as over s. Okay, so this is our basic guiding formula. What's our issue here? The issue is this inside part doesn't look like u of t minus a here. And here we have products. And unfortunately, just like with integration, products can get kind of tricky. So what are we going to do? Well, here's what I recommend. Is to say, well, let's think about what this function is doing. Where do the on-off switches occur? So to figure that out, let's go through every single piece. We'll start here. This one is fairly easy. This has an on-off switch where? So this happens, the on-off is at t equals 2, right? Where is that 0? 0 is where you switch. Because the picture, if we were to graph our u of t function, it says I'll just graph u of t minus a. So here's A. So you're 0, and then you're 1. So you're switching behavior. And all right, so find out where the inside is 0. That says where you flip your switch. How about here? 5 minus t. Where do we turn on or off? That happens at t equals 5. Now this one, where does this happen? On, off. Well, that's minus t squared plus 10t minus 21 equals 0. If you factor the minus out, that's t squared minus 10t plus 21 equals 0. And that factors as t minus 3, t minus 7. And so in particular, on-off happens at t equals 3 and t equals 7. Okay, so we can say that interesting things happen at 2, 3, 5, 7. So let's figure out what's going on. What's going on? What's going on? So I'm going to mark 2, 3, 5, 7. And my question is, what is the value in each one of these pieces? So let's start with something below 2. So we can start with 0, that's below 2. Here you have a negative number, off. Here, that's negative, off. And off times anything is off, right? Because off is 0. So before 2, we are 0. Between 2 and 3, so like 2.5. Well, if you plug it in, and you're like, oh, I don't know, I'll plug it in over here. That's easier to see. If you're at 2.5, 2.5 minus 3 is negative. 2.5 minus 7 is negative. There's one more negative. 3 negatives means you're negative. So you're off. So that's still off. Here, 2.5 minus 2, positive, you're on. Here, 5 minus 2.5, positive, you're on. So what's the net contribution? 2 minus 6. So we are minus 6. Between 3 and 5, what's going on? Well, pick a number like 4. Now you can plug 4, and you can, if you do the factored form, it's pretty easy. 4 minus 3 is positive. 4 minus 7 is negative. Minus plus minus is a plus. So we are on. So that's a 2. Here, 4 minus 2 is positive. 5 minus 4 is positive. You're on here. So on. 2 minus 6 means it's negative 4. How about between 5 and 7? All right, well, pick something like 6. And we're testing. We plug it in. 6 minus 3 positive, 6 minus 7 negative, negative, positive, negative. And that result positive. We're on. Plug in 6 here. 6 minus 2, positive, on. 5 minus 6 negative, off, right? So if either piece is off, we're off. So we say, oh, so this is now completely turned off. Okay, so what's left? Just the 2, right? This is on, this is at off. What if you're bigger than 7? So plug in a really big number, like 8. All right, million, but 8 works. 8 minus 3 positive, 8 minus 7 positive, but then there's a negative. So this has been turned off. 8 minus 2 is positive, but 5 minus 8 is negative. That's turned off, so this is off. So we're back down to 0. So there we go. So our function that we're trying to understand, it starts 0, goes down to negative 6, up to negative 4, up to 2, then 0. Now, we haven't yet gone to the point where we can talk about the Laplace. But what we can do is say, we better understand our function. Now what we'll do is, let's rewrite our function. And we just say, okay, this is the same as the Laplace, and now we're going to rewrite it using this information. Well, we start at 0, so we say 0. Well, we oftentimes don't write down the 0. And then our first on-off happens at 2. So we're going to have our u of t minus 2. And now, what needs to happen? Well, we need to go from 0 to negative 6. So we're going to multiply this by negative 6. All right, so that handles the first transition. Plus u of t minus 3. Now here, what's going to happen? We need to go from negative 6 up to negative 4. How do we do that? Well, to get from negative 6 to negative 4, we need to add 2 more. So add 2. Right? So once we pass 3, they're both on. Right? We just keep turning more switches on as we go from left to right. Then we go to 5. U of t minus 5. So, all right, well, we need to go from negative 4 up to 2. How do we do that? Well, that would be an increase of 6. So I'd say, okay, add 6. So again, think about the net effect. On, all combined together. And now we're at 2. We come to our last switch, which is at 7. And that's going to go from 2 down to 0. Well, how do we get from 2 to 0? Minus 2. And if you notice, what are these numbers that we're putting here? They are our change, right? So net change of negative 6, net change of positive 2, net change of positive 6, net change of negative 2. That's what's going on. All right. Well, now we are in the state, we can write down our answer. Because we can use linearity and we can use our nice fact. So the main work in this problem is actually just rewriting it in a nice way. So we don't have products, or we don't have some big expression inside of u. So we have negative 6. U of t minus 2 would be e to the minus 2s over s. And then we have plus 2, u of t minus 3, e to the minus 3s over s. Plus 6, u of t minus 5, e to the minus 5s over s. And our last one, a minus 2, and then u of t minus 7 goes to e to the minus 7s over s. And we're done. That's the Laplace transform. That's what we needed to find. And so life is good. All right. Again, what's the main challenge? Main thing that we need to do to solve this problem? We need to rewrite this in a way so we can use our basic formula. And that's how a lot of this works. Can you say, let me get it ready so that I can use my table? That's why it's good to know your table. So you know what target you're shooting for. So you're not just randomly, grasping at straws in the dark. No. The table gives us light. It helps us see where we need to go. And so let's make sure we're good and ready to use it. Number 4. Find the Laplace transform of, and it's a lot, the sum k equals 0 to infinity, 5 to the k, u of t minus k. And then if that wasn't enough, express your final answer without using an infinite sum. What? This is crazy. All right, but interesting. Because the original function does have an infinite sum. Now, the nice thing is an infinite sum is a sum. It has the word in it. It says sum. So, you could say that it's a something. All right, so what can we do? Well, just say, let me proceed, right? So I can use linearity. 5 to the k, that's a constant. Use linearity. So we say, all right, using our linearity, trusting the process. This becomes the sum, 0 to infinity, 5 to the k times the Laplace of u t minus k. All right, I trust the process. And we grab our formula sheet. It's a very nice formula sheet. And we say, u of t minus a, e to the minus as over s. So we just say, okay, u of t minus k, e to the minus ks over s. All right, so we say this becomes our sum, k equals 0 to infinity, 5 to the k, e to the minus ks over s. All right, nice. We have done the first part. So, are we done? No. Because we have the second command, right? Express your final answer without using an infinite sum. We definitely have an infinite sum there. So we start saying, okay, what can we do? What can we do? And we say, well, let us ponder and think, is there anything on our formula sheet which can help us? And it turns out that in this lower left corner, there is something that's very tempting. Two sums. Two infinite sums. And so we say, oh, well, maybe one of these can work. Now there's what we call geometric and exponential. Geometric says if you're adding up something to the k power from 0 to infinity, 1 over 1 minus the something. The exponential says something to the k over k factorial. You add it up from 0 to infinity, you get e to the z. Now, notice what we don't have. There's not a factorial here. So we're like, oh, so that means geometric. So we have, for reference, for geometric, we know that the sum, k equals 0 to infinity. And I'm going to, instead of writing as z, I'm going to write it as something to the k is 1 over 1 minus something. And now we get to the age-old question. What's in the box? What's in the box? Right? That's the question. What fits in this box? If we can answer that, we're done. So we look at our situation here. We say this S, that doesn't involve K at all. That can come out. All right, so let's go ahead. Let's take it out. Let's do that. Let's do that. So we have 1 over S, our sum, K equals 0 to infinity. We have 5 to the K. Now, this other term, e to the minus ks. See how there's k's in two places? We want to get it to 1k. And not only do we want to get it to 1k, we want to get to something to the k. Now, the question, can we express e to the minus ks as something to the k? Because if we can, that's good news. And if we can't, we need to try again. But now we say, well, hey, this is exponents. And there's nice rules about exponents. And one of the nice rules about exponents is if you have multiplication, that indicates power to a power, right? We're looking for the higher power, the power upstairs. And in particular, say, okay, I claim this is e to the minus s raised to the kth power. Now, convince yourself, right? If you think of the rules, if you have a power to a power, multiply the powers, that does become minus ks. But since both of these are to the power k, we can combine. So we have 1 over s, sum, k equals 0 to infinity, 5 e to the minus s to the kth power. we know the answer. What's in the box? The answer is 5 times e to the minus s. That's what's in the box. And we're like, yes, that can help us. Our answer is a hop, skip, and a jump away. So what do we end up with? We end up with 1 over s times 1 over 5. Let me try this again. That's 1 over s times 1 over 1 minus 5e to the minus s. And there we go. That is a perfectly valid way to write it. We could do a couple of other manipulations, but that is our answer. And there's no infinite sum involved. Life is good. Life is wonderful. It's nice to see sums again. It's been a while since we've seen these sums. And that should be something to celebrate, right? Okay, all right. Let's keep going. On to the next one. Number 5. We need to find the inverse Laplace of 50 minus 15s divided by s over s squared plus 25. All right, so what do we do? Well, this is a chance for us to do partial fractions, right? That's actually going to be a very common thing for us. So we want to make sure we're comfortable with partial fractions. Really, what are we doing? We're trying to get to the stage where we can use things in our formula sheet. But if you look at our formula sheet, it's not very good at handling things where there's a product going on downstairs. So we would like to say, let's pull things apart. Pull them apart so that life is good. So most of our work is going to be algebra, and then there'll be a little bit of work on the end where we say, okay, now let's apply our formulas. Let's look at our table. Okay, so algebra interlude. We're going to go into partial fractions. And the nice thing for us, they've already factored it for us. So that's good news. So we say, all right, well, we have our 50 minus 15s. We definitely need those pieces. Divide by s times s squared plus 25. And in addition to saying, make sure you can distinguish your 5s from your s's, because that's going to be really confusing on this one, right? If you're not careful. So that's an s, that's a 5. Pay attention. But also, make sure you do algebra correctly. There are some people who say, oh, why don't we just cancel an s, right? Because there's an s here and an s there. Is that allowed? Notice I didn't write it. Could you do it? No, you can't. Not allowed. Don't be creative at this stage. You know, I love your creativity. That's a beautiful thing. But at this stage, I want you to be like, I'm following the rules. And the rules say if I do any cancellation with upstairs and downstairs, it has to involve multiplication on the whole thing upstairs. That is not what you have. So you can't just cancel that s and that s. All right, well, what are we going to do? Well, partial fraction says, since we already have the denominator factored, we're going to pull this apart. So that's the nice thing about partial fractions. You're pulling things into smaller, more manageable, bite-sized pieces. And the key is, well, what goes upstairs? Over the s, we'll have some unknown value. We'll call it a. Over s squared plus 25, some unknown values. We'll call them b, s, and c. So there we go. Now the main work is, what is a, b, and c? Now, a quick sanity check to see, did I get partial fractions right, is to say, what's your degree in your denominator that you started with? It's degree 3. How many things am I solving for? 3. Those numbers should match. If they don't, mistakes in your setup have been made. Double check your work. Because if you can't get the right start, you won't get the right finish. Well, all right, now where do we go? We're going to multiply to get rid of our denominators because we want to get to polynomial equals polynomial. So I'm going to start with my original denominator. That's going to completely cancel on the left-hand side. So we get 50 minus 15s. Over here, the s's cancel. So we'll get a times s squared plus 25. Here, the s squared plus 25's cancel. And we're going to end up with bs plus c times s. Well, are there any good choices? Because that's a strategy. Can you think of a good choice? Now, you might say, well, what's a good choice? A good choice is something which zeroes a lot of stuff out. So 0 is our friend. And I look and say, well, if I could zero that out, that would really simplify things. So it looks like there's a good choice to start with. And let's go ahead and just do that while we're at it. Sometimes it helps, sometimes it doesn't, but at the very least, it's progress. I plug in 0. 50 minus 0, that's 50. We'll get a times 0 plus 25, so 25a. And then we'll get b times 0 plus c, all of that times 0, that's all gone. So now we know, aha, a equals 2. Cool. So that part is 2. And by the way, make sure you know which thing goes with which number. I have seen too many students correctly solve for these coefficients, but then not put them back in the right place. All right, so we know A. How to get B and C? Well, that's a little bit harder. But here's what we can do. Let's go ahead and multiply out and gather, right? Because when are two polynomials equal? And there's not one correct answer. There's actually many correct answers. One thing is they have to match at points, and that's why you make good choices. Another is you say, oh, coefficients have to match, and that's your go-to, right? If you can't think of anything else, match your coefficients. So let's see what we have. In terms of s squared, I have an a and a b. So we have an a plus b s squared. In terms of s, there's no s terms here. Here there's a c times s. So plus c times s. In terms of constant, well, not constant, not constant. Here is 25a. And now we say, well, here are two polynomials. The coefficients must match. So we say, well, constant 50 has to match with this constant. So this part has to equal 50. The coefficient of s has to match this coefficient of s. So that has to be negative 15. And then the coefficient for s squared, wait, there's no s squared. Well, there kind of is. It's 0 s squared. So if you don't see an s squared, there's always a 0 floating around. That says that this part has to be 0. And now we're like, oh, a equals 2. Yep, we already knew that. But what else? C is negative 15. Hey, there's something. Cool. So C, this is negative 15. And now a plus b is 0. So b is minus a. But a is 2. So b is minus 2. So, all right. So there's b, minus 2. Now, what does this give us? It gives us a way to rewrite. So let's update what we were trying to do. We're trying to do the inverse Laplace and our work with partial fractions. Good work. Very happy with what we did. This says that this is equal to inverse Laplace of upstairs, let's just follow along here, 2 over s plus a minus 2s minus 15 over s squared plus 25. Now, we can take advantage of this, right? We see s squared plus 25, so there's no shift. So we'd like to have things with just s and things with just a constant. So let's do that. So I'm going to put a minus 2 times s over s squared plus 25. And then plus, and let's be careful here, 25 is 5 squared. So if I was doing a constant, what constant would I want upstairs? I'd want 5. Why do I say that? Because I'm looking back at the formula sheet, and I say, oh, I see s squared plus 5 squared shows up as sines and cosines. So I'd want to have something with s and something with the b, right? B squared, b upstairs. So I'd want the other term to have a 5. Well, right now it's going to have negative 15. So I'm going to pull out negative 3 and write a 5 over s squared plus 25. Now, we're in good shape. Well, what can we do? We'll go ahead. We'll apply our linearity. So this becomes 2 inverse Laplace of 1 over s minus 2 inverse Laplace of s over s squared plus 25 and minus 3 inverse Laplace of 5 over s squared plus 25. And now we can handle each one. Inverse Laplace of 1 over s? Yes, that's on our formula sheet. There's 1 over s. Inverse Laplace would be 1. And so we say, okay, so this is 2 times 1, that's 2. Minus 2, s over s squared plus 25. S over s squared plus 25, that's s over b is 5. So that's cosine 5t. Okay, so this is cosine of 5t. And then similar, this will be sine of 5t. And there we go. That's our answer. We're done. We did it. Woohoo! Yay, us. Good job, us. All right. I'm sure we'll get to do some more practice with partial fractions. So let's keep moving forward. Number 6. Find the inverse Laplace of, we have 2s plus 8 divided by s plus 1 times s plus 2 times s plus 3. All right, well, partial fractions, right? We don't even have to, of course, we got to pull this apart. And we see they were very nice to us. They factored because our professors, they like us. And we like them. All right, well, so let's start. And so most of this work is going to be the partial fractions. And at the end, we're just going to be pew, 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 and then we'll be done. Okay, so we haven't gone to the pew, 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 pew part, so let's do our partial fractions part. All right. Now, what do we have? 2s plus 8 divide by s plus 1, s plus 2, s plus 3. Well, we're going to have 3 pieces, one for each term down here. So there's going to be something over s plus 1 plus something over s plus 2 plus something over s plus 3. Now what goes upstairs? Well, unknowns. And these are linear terms, so our unknowns look like numbers A, B, C. And so our goal, what are A, B, and C? If we have that, then we have our partial fraction decomposition. Life is good. So to get there, we'll say, all right, let's first off clear our denominators. So everything gets multiplied by s plus 1, s plus 2, s plus 3, our original denominator. If we do that, all of it's gone on the left-hand side. So 2s plus 8. In the first term, the s plus 1's cancel. So we have a times s plus 2, s plus 3. In the second term, the s plus 2's cancel. So we're going to get b times s plus 1, s plus 3. The last term, the s plus 3's cancel. So we're going to end up with c times s plus 1, s plus 2. All right. Now, we could do a lot of work expanding and collecting coefficients. But how about we do, instead, making good choices? So, what are some good choices? In other words, what are things that make some of these terms go away? And, well, you can kind of think of what makes these terms 0. I think -1 would be a good choice. Let's try it. Why? Because I see an s plus 1 term here and here. When I plug in -1, those terms go away. So in particular, we have minus 2 plus 8, which is 6, is equal to a times 1 times 2. So that would be 2a. All right, that says a should be 3. Yes? Right, 1 times 2. Good, good. Well, that was quick. Is there another good choice? Well, I see some s plus 2's, so let's make those disappear. Let's choose s equals minus 2. Minus 4 plus 8, well, that would be 4. 0, because that's going to go away. 0 on the end, so we have a b. And then minus 2 plus 1 is a minus 1, and a minus 2 plus 3 is a plus 1. So we'll get 4 equals b times minus 1. Well, that says, hey, b is -4. All right, good. Progress, a lot of progress. Very quick progress. We like that. And, well, okay, we see some s plus 3's. So let's choose s equals -3. Minus 6 plus 8 is 2. The s plus 3 makes that first term cancel when we plug in -3. Similarly, it makes the second term cancel. So we have c minus 3 plus 1 is a minus 2. Minus 3 plus 2 is a minus 1. So that's actually a 2c. 2 is 2c. That says, oh, c is 1. All right, so now we know these values. C is 1. And then we should have written this down earlier. We'll do it now. This b is -4. And finally, we say, aha, this a here is 3. Now we're ready to do what? Well, we're ready to rewrite our problem. So we've did our partial fractions work. Thank you. Thank you. And we'll put that to the side. And that says this can be rewritten now as find the inverse Laplace of 3 over s plus 1 minus 4 over s plus 2 plus 1 over s plus 3. And we can do linearity. So this is 3 inverse Laplace 1 over s plus 1 minus 4 inverse Laplace 1 over s plus 2 plus inverse Laplace 1 over s plus 3. And very conveniently, these aren't just any random things, but they are things on our formula sheet. Yes, they're ones we should know. In fact, they're one of our most important rules. Laplace of e to the something t, 1 over s minus something. Now notice these are plus somethings, so what's going on is that we have to use, like plus 2 is like minus 2, and so forth and so on. So in particular, we say, well, this first one, This is s minus minus 1. This will become an e to the minus t. S plus 2 minus minus 2, e to the minus 2t. S plus 3 minus minus 3, e to the minus 3t. Giving us our final answer is 3 e to the minus t minus 4 e to the minus 2t and plus e to the minus 3t. And there we go. Life is good. Life is wonderful. Yes. Yes, it is. Number 7. Find the inverse Laplace of 3s squared minus 18s plus 26 divided by s minus 2 cubed. Okay, nice. So what are we going to do? Partial fractions? Again? Yes, we got to get good at it. So we're going to practice it. So, all right. So let's do it. Once more to the breach, dear friends. Once more. All right, so here we go. We're doing our partial fractions. And what can we do? Whoops, partial fractions we can spell. Yeah, of course we can. We're pros at spelling. That's why we study math. Well, we're going to start with our 3s squared, subtract 18s, add 26, divide by s minus 2 quantity cubed. Now, notice, you're like, oh, wait, there's only one thing downstairs. Yes, but what's the power? Cube. So when we do partial fractions, when we pull it apart, we've got to build up our s minus 2's. So what will happen is we're going to get something over s minus 2 to the 1 plus something over s minus 2 to the 2 plus something over s minus 2 to the 3. Now what goes upstairs? And this is a point where some people struggle, but let's be really clear. When you're cluing on what's downstairs, you don't clue on this part right here, this 2 or this 3. What you're cluing in on, what's inside the parentheses. In each case, it's what we call a linear term, something with just an s. So that says the terms upstairs will be constants. When in doubt, think back to your rule. What's the original degree of your denominator? 3. So how many unknowns should we have? 3. If we have more than 3 unknowns, mistakes were made. So, okay, so that's good. We have our setup. Well, where to from here? We need to clear our denominators. So let's do that. So our original denominator is s minus 2 cubed. So everything's getting multiplied by s minus 2 cubed. So we get 3s squared minus 18s plus 26 is a times s minus 2 squared plus b times s minus 2 plus c. Yes? Right? Because here, all of the terms cancel. 2 of them cancel, so there's still 1 left. And only 1 cancels, so there's still 2 left. Now, we can make good choices. Well, there's one really clear choice, which is plug in 2. So we say, all right, we plug in 2. S equals 2. What will that give us? Well, it gives us 3 times 4 is 12. And then minus 18 times 2, 36. And then add 26. And, well, minus 36 plus 26 is minus 10. And then plus 12 would give us a 2. Okay, so that's not too bad. All right, now that's the left-hand side would be 0, 0, C. So 2 equals C. Nice. Good. Good. We figured out C. Okay, so C here is 2. But now what? Well, here's a fun thing that we can do. We have polynomial equals polynomial. There's lots of ways to get your answer. So find something that you're comfortable with, because ultimately you're the one who has to do it. But when you're in a case where you have like s minus or s plus something to a high power, one thing that can work really well is use derivatives, because two polynomials agree if and only if their derivatives agree. And so why take a derivative? Well, let's take a derivative and we'll see if we get some insight. So the derivatives have to match. Take the derivative of the left-hand side, 6s minus 18, that goes away. Here, you'd have 2a times s minus 2 plus b and 0. Now, what can you do? Well, we can plug in 2. You might say, well, wait a second, we plugged in 2 before. Well, we plugged in 2 before the derivative. This is after the derivative. Here we'll get 12 minus 18 is negative 6. Here we're going to get 2a times 0. And here we'll get b. So what do we conclude? We conclude b is negative 6. Like, great, now we have b. All right, well, what can we do now? Well, we have an idea so nice, let's use it twice. Let's take another derivative. What's the derivative of 6s minus 18? 6. What's the derivative of 2a times s minus 2? Well, 2a is a constant. Derivative of s minus 2? 1. And then what's the derivative of b? 0. So we get down to this 6 equals 2a. Oh, we don't even have to plug anything in. That says what? A equals 3. And so there's our last term. And now we solve for a, b, and c. And so we're done. We're done with partial fractions. So this sort of fun little toy, matching derivatives, works especially well when you have something like s minus something to a high power. It doesn't always work, but you know, it's fun to think about things which can work in special cases. It's good to see different ideas. So now let's update what we have. So we have, this is the inverse Laplace of 3 over s minus 2 minus 6 over s minus 2 squared plus 2 over s minus 2 cubed. Okay, well, before we pick up again, let's think about what rules do we need. What do we see going on with our terms? We see shifts, right? Because it's not just s, it's like s minus 2. When we see shifts in s, we have this rule here. So I'm going to write this rule down for our reference. It says the Laplace of e to the b t f of t f of s minus b. So here we have a shift of 2. So it says, oh, our terms are going to have an e to the 2t attached. Okay, so we're anticipating our answer should have e to the 2t's. But now, let's say there wasn't a shift. How do we take the inverse Laplace of s cubed in the denominator? So we say, okay, start scanning. Where is something that looks like an s cubed downstairs? Aha, here's another rule. Let's write that rule down. If we have t to the n, that looks like n factorial over s to the n plus 1. So here's the idea. Let's see what we have. We want to make these pieces match here. So s minus 2, well, actually that one we can just use, there's a nice formula for exponential function. So I'm just going to say that's 3 inverse Laplace 1 over s minus 2. Now s minus 2 squared, that would be a square, is n equals 1. So we want a 1 factorial upstairs. 1 factorial, also known as 1. Okay, so this 6 I can pull out. So minus 6, inverse Laplace, 1 over s minus 2 squared. Now, s minus 2 cubed. S cubed would say n equals 2, right? 2 plus 1 is 3. So we want a 2 factorial upstairs. Now, the good news is 2 is like a 2 factorial. So I'm going to write this as a plus inverse Laplace 2 factorial over s minus 2 cubed. Now, we just need to write down our answers. So, 1 over s minus 2, I'm just going to point out it's on our formula sheet, 1 over s minus b, e to the bt. So, this would be, by itself, is e to the 2t. Notice you can think of it if you plugged in n equals 0. So you took the Laplace of t to the 0, which is 1. Well, that would be 0 factorial, which is 1 over s to the 1. And so you say, 1 over s would go to 1. So there's a nice consistency that goes on. Now here, s squared. Well, first off, the shift, that tells us e to the 2t. And then it's like, well, now imagine taking the inverse Laplace without the shift. We say, well, without the shift, that would become just t. Right? Inverse Laplace of 1 over s squared is t. Again, if you see the shift, that says, oh, we're going to have an e to the 2t. But now imagine what happens if we don't have the shift. Well, if we don't have the shift, that would become, if you look here, the rule for n equals 2. So that would become an e to the 2t t squared. So when we put it all together, what do we have? We have 3 e to the 2t minus 6, and I'm just going to write this in the other order, 6t e to the 2t, and then plus t squared e to the 2t. And there we go. That's the answer. All right, good. So be comfortable with mixing rules, right? Especially if you see a shift, it means you add an exponential function and figure out what happens without the shift. Practice. Practice with the rules until they become so familiar. You don't have to think about it. It'll become reflexive, automatic. Life will become more fun. All right, let's keep going. Number 8. Use Laplace transforms to solve the differential equation. X double prime minus 5x prime plus 4x equals 0. And some initial conditions. X is 0 is 3, and x prime is 0 is negative 3. Now notice this is actually a really nice differential equation. Constant coefficient, linear, homogeneous. Those are things we really like about differential equations. We already know how to solve them, but here we need to use our new tools because we want to get comfortable with our new tools and say, okay, so we're going to focus on a Laplace transform way to go about solving this problem. So what's our mindset? Well, there's a very simple philosophy. It says, if I start with two things which are the same, and then I do the same thing to them, I get the same thing out. And okay, that seems reasonable. So here we have two things which are the same. That's what equal means. So we're going to do the same thing to them. And that thing that we're going to do is we're going to take the Laplace transform. So we have that the Laplace transform of the left-hand side, x double prime minus 5x prime plus 4x, is equal to the Laplace transform of the right-hand side, of 0. Now, the Laplace transform of 0 is, very unsurprisingly, 0. Well, what about this other side? We can start by linearity. We get Laplace transform of x double prime minus 5, Laplace transform of x prime, and plus 4, Laplace transform of x. But now we're like, but yeah, where do we go here? And we say, well, the Laplace transform of x, we'll give that a name. We'll call this capital X. And we want to, try to make sure we are consistent in making that look like a capital X so we don't get confused. But what about these other two? Wouldn't it be nice if there was a formula? Yes, it would be really nice. Is there a formula? Yes. And that's actually right near the bottom. It says, if you take the Laplace of a derivative, you add a factor of s, and then there's this correction. If you take the Laplace of the second derivative, you have an s squared, and again, some correction. And these are where initial conditions come in. Now, this is phrased in terms of f. It can be any function, so we'll use x. So I'm going to rewrite these in the corner just for reference. So we have that the Laplace of x prime is equal to s capital X minus our little x of 0. And Laplace of x double prime is s squared capital X minus s x of 0 minus x prime of 0. Okay, so there we have them in the corner for reference. And notice something. These are our initial conditions. Initial conditions come in at the start, not at the end. It used to be that when we solved the differential equation, we would go through and then we'd wait till the very end, and then we say, okay, now let's worry about initial conditions. Here we say, we're not going to do that at all. We're going to put them in at the start, and then they take care of themselves. So that's an interesting thing. All right, now let's update what we have. So Laplace of x prime, according to what we have, will be what? Well, it will be, s capital X minus 3, right? X is 0. So minus 3. Okay, what about Laplace of x double prime? Well, that will be s squared capital X, cool, minus s times x0 minus 3s minus x prime is 0 minus 3 is a plus 3. All right, I'll add the coefficients, and we're up to here. Now, the next thing to happen is we're going to put things together. So I'm going to be very careful and distribute. Don't forget parentheses. They're our friends. They help us make sure we get everything. And so what do we have? When we put all of this together, well, let's look at the things which involve x. There's 3 pieces which involve x. And what do we have? Well, we're going to get an s squared, a subtract 5s, and we're going to add a 4, right? S squared minus 5s plus 4. And that's going to be multiplied by x. All right, good. I'm going to pause for a second. This s squared minus 5s plus 4, Does it sound familiar? Would we have seen something like this before in perhaps a slightly different context? Notice our differential equation, x double prime minus 5x prime plus 4x. That looks an awful lot like these coefficients. And if you were to do the characteristic polynomial, you would get this polynomial. Coincidence? No, it's not a coincidence. So, okay, all these things, they come together. It's like, hey, there's patterns. And when you start to pick up on the patterns, life is good. All right, now we're not done yet. What's left? Well, we got to gather the s terms. There's just one of them. So that'll be pretty straightforward, minus 3s. Then the constant terms, you have a plus 3, and then a minus 5 times a minus 3. That's a 15. So 3 plus 15 is 18. All right, and remember, all that equals 0. All right, good. Well, our goal is to solve for x. Now, note s squared minus 5s plus 4. That looks like it factors. We need two things that multiply to 4, add to negative 5, and let's try it. I think s minus 1, s minus 4 does it. Let's check. S squared, good. Minus 4s minus s is minus 5s, and a plus 4. And these terms we move across, so when we move them across, 3s subtract 18, and now we get x is 3s subtract 18 divide by s minus 1, s minus 4. And you're like, cool, we're done, right? Well, we're a lot closer. We're trying to solve for little x. We solve for big X, in a sense. Well, what is that? Well, what we're saying is that the Laplace transform of our answer is this expression. So how do we get our answer? We need to un-Laplace it, or we need to take the inverse Laplace. So we say, okay, well, how are we going to do that? We need to do something to simplify this expression. We're going to partial fractions it. Yeah. All right. Right, we're going to get really good at partial fractions. Okay, so we come here and say, all right, our work in solving our differential equation has changed slightly. Partial fractions is now our go-to algebra tool. So we have 3s subtract 18 divide by s minus 1, s minus 4, which is already nicely factored. We're going to pull it into two pieces, an s minus 1 piece and an s minus 4 piece. Upstairs, well, we're going to have something above s minus 1 and something above s minus 4. We need to figure out what are the a and the b that'll make this work. So we begin and we say, well, let's first off get rid of our denominators. So we multiply both sides by s minus 1, s minus 4. And if we do that, that leads us to the following. 3s subtract 18 will be equal to, here the s minus 1's cancel, so we're going to get a times s minus 4. And here the s minus 4's cancel, so we're going to get b times s minus 1. Now, I like to make good choices, like reviewing for the quiz. Excellent choice. But here I'm specifically saying, what are some values for s that'll give me zeros? Well, I notice here I have an s minus 1. So I think if we plug in s equals 1, that can help us knock some terms out. 3 subtract 18, negative 15. 1 subtract 4 is negative 3. So minus 3a, and then that's 0. Well, that says, oh, A should be 5. Okay, so now we know A is 5. But we can make another good choice. Say, well, let's knock out the other term. Okay, so what would do that? 4 could do that. So let's plug it in. So we plug in 4. S equals 4. What happens? 12 minus 18, negative 6, equals 0. And B times 3. 3B. So that says, oh, B should be negative 2. All right, so B is minus 2. So now we go back. We've done our partial fractions. We've done our algebra work. We use that to rewrite our expression. This is going to become 5 over s minus 1 minus 2 over s minus 4. And now our final answer, well, our x of t, our solution, that's the inverse Laplace of capital X. And so we're taking the inverse Laplace of this. And these are nice ones. We're like, wow, these are ones that we're using so often, we may even have them memorized. So I'm going to use linearity. Then I'm going to grab my formula sheet and say, aha, s minus something downstairs means exponential. So in particular, this first term, 1 over s minus 1, would mean e to the t. The second term, 1 over s minus 4, e to the 4t. And so our final answer, we have 5 e to the t subtract 2 e to the 4t. And we're done. We did it! Woohoo! Yay, us! Good job, us! All right. Now, can we check our work? Well, there's a few things we can check which don't take very much. Let's check our initial conditions. When you plug in 0, do you get 3? 5 minus 2, 3. Check. How about the derivative? Well, we can do that almost in our head. That would be 5 e to the t, subtract 8 e to the 4t, plug in 0. 5 minus 8, negative 3. Check. Like, all right, that's a good sign. Now, I'm going to tell you this. This is my second time working through this problem because I got to an answer and I did my checks and I was like, whoops, I was not satisfying my initial conditions. So I knew I had made a mistake. And so I said, okay, I know my answer is wrong. So let me find my error. It turned out I had done some incorrect work simplifying. And so I redid the problem. So, don't feel bad about making mistakes because they happen, but don't let them slip by. Do your best to catch them. Once you know you've made a mistake, here's the great thing. You'll find it pretty quickly. It's the mistakes that you don't know about that are really hard to find. So think about, can I check my work? Have I done this correctly? Look for ways to correct yourself. As the great mathematicians would say, you should check yourself before you wreck yourself. All right. On to the next one. Number 9. Find x of s, which is the Laplace transform of x of t. We're given x double prime plus 3x prime plus 2x is 2 e to the 4t minus 3 u of t minus 3 and some initial conditions. Now, let's be clear. We are not asked to solve this differential equation. We're just practicing at this stage, rewriting and saying, oh, let's transform this differential equation into the algebra equation. So we need to know a couple of things. Let's gather our rules that we're going to need. We'll put them together down here. what are some things we see? Well, I see x double prime and x prime. So there's some rules about x prime and x double prime. So I'm going to write those down. Those seem like they'll be good to have on reference. So x prime, according to the rule, is s capital X minus x of 0. For x double prime, that would be s squared capital X minus s x of 0 minus x prime of 0. All right, so that's going to help us on this side. We see an e to the 4t, and that's right here up in the corner of our screen. And so the Laplace of, and I'll write down our rule, e to the bt is 1 over s minus b. Okay, that'll help us there. And then there's this u of t minus 3. And u of t minus 3, that'll be the rule right below it. The Laplace of u of t minus a is e to the minus as over s. All right, so those are the pieces that we see here. So we've written those down. So now we're ready. All right, and no big surprises. What are we going to do? We're going to take the Laplace of the two sides. So we take the Laplace of the left. That's got to match the Laplace on the right. And then we just start solving for capital X. All right, so let's go through and do this term by term. So I'm going to go ahead and use linearity right from the beginning. So the Laplace of x double prime plus 3 Laplace of x prime plus 2 Laplace of x is equal to 2 Laplace e to the 4t minus 3 Laplace of u of t minus 3. Okay, so we took Laplace on both sides. Though the result will still be equal, we use linearity to break things up. Now we go through term by term. So x double prime. This will be s squared capital X, which is what we're going to solve for, minus s times x is 0. So minus s. Minus x prime is 0. So minus 2. Right? Be careful. If your s's look like 5s, you might say, oh, here's a 5. No, that's an s. Make sure you know. All right, then we have plus 3. Parenthesis, the Laplace of x prime. S capital X minus x of 0. 1. Parenthesis, plus 2. Laplace of x is capital X. Is equal to, well, 2. And then the Laplace of e to the 4t, 1 over s minus 4. 1 over s minus 4. And then minus 3. Laplace of u of t minus 3. Well, what is that? Okay, a is 3. So that would be e to the minus 3s over s. So, all right, e to the minus 3s over s. Well, we can now gather. So let's gather our capital X terms, right? There's 3 of them. So we have one here, and here, and here. All right, so that would be, don't forget to distribute. So we have s squared plus 3s plus 2 capital X. And then, well, we have a single s term, minus s. Then we have a minus 2 and minus 3, right? Minus 2 minus 3 is, a minus 5. Okay, well, all right, make sure we distinguish. And still have the other side. 2, 1 over s minus 4. and minus 3 e to the minus 3s over s. We can take these terms, pull them across. So we get s squared plus 3s plus 2 capital X is equal to, well, just to help simplify writing, 2 over s minus 4 minus 3 e to the minus 3s over s plus s plus 5. And now I want to get x by itself. So capital X is equal to 1 over s squared plus 3s plus 2 times 2 over s minus 4 minus 3 e to the minus 3s over s plus s plus 5, and we can stop. Why? Because we did what the problem asked us to do. The problem was find x of s. That was the goal. And we did. Here's x, so we got x by itself. And so we can box it. Or we could do more work, but I'm of the opinion, let's not do more work if we don't have to. So there we go. Our lovely answer. Whew. All right. Well, not too bad that once you know your rules and you just carefully, methodically apply everything. Take the Laplace of both sides, group your x's together, get everything else on the other side, and then divide by what's in front of x. And life is good. Life is wonderful. Number 10. Woohoo! Number 10. We're asked to find capital X of s, the Laplace of x of t. We're given x of 0 is 2, x prime of 0 is negative 3, y of 0 is 1, y prime of 0 is negative 4, and we have a system. We have x double prime plus 3y prime minus 2y equals 0, 2x prime minus 3x plus 4y double prime equals 0. So here we say, oh, what's going on? Now, there's a couple of ways we could go about doing this. One is we could say, well, let's get a single differential equation for x using tools that we've done before. And once we have such a thing, then we take the Laplace and we are good to go. But I want to do it in a more Laplace-centered way because I want to show you, hey, Laplace can handle systems. So what would be the Laplace way to approach this? Well, what formulas do we need? What functions are showing up? Or what rules come into play? There's 2 rules. And there's no function showing up. There's no e to the t, sines, cosines. But we do see a derivative and a second derivative. So I'm going to write those rules down. I'm going to write them down as they're written here on the formula sheet because I want to emphasize what's going on. So the Laplace of a derivative f prime is s capital F minus f of 0. All right, technically I'm not writing it down exactly as the formula sheet, but, close enough. The Laplace of the second derivative, s squared capital F minus s f of 0 minus f prime of 0. Okay. And notice we really don't care whether our f is x or y. So what do? We just plug it in. In other words, we're going to take the Laplace of both sides on both equations. So let's write that down. We have 0, which is the Laplace of 0. Well, that's the Laplace of x double prime plus 3 Laplace y prime minus 2 Laplace of y. Well, what do we do with our x double prime? Well, that's f is x. So that would be s squared capital X minus s x 0. So minus 2s minus f prime 0, or x prime 0, minus 3 plus 3. That's the first term, plus 3. Now, Laplace of y prime. So here, f is y. So that would be s capital Y minus y of 0. Y of 0 is 1, so minus 1. Minus 2 capital Y. All right. Well, let's clean this up, and then we'll do the other one. So, first things is we have one x term, and we have two y terms. So I'm going to note that there. So if we gather the x's and the y's, what do we have? Well, we have s squared times capital X, and then for y, we get the 3s and a minus 2. So plus 3s minus 2 capital Y. What's not yet accounted for? Well, we haven't accounted for this minus 2s. Let's move that to the other side as a plus 2s. We also have a plus 3, and here we have a minus 3. Plus 3 minus 3 makes 0. They cancel. Ha ha ha. Woohoo. Nice. Okay, so that's it. We've accounted for everything. We got the x and the y terms. The constant terms canceled. The minus 2s moved across. That's the first formula. Well, that was so nice. We're going to do it twice. So our second formula, we have that 0 is the Laplace of 0. Well, okay, that's the Laplace, well, 2 times the Laplace of x prime minus 3 times the Laplace of x plus 4 times the Laplace of y double prime. Well, okay, let's start with our first term. We have a 2. Laplace of x prime is s capital X minus x of 0, minus 2. Minus 3, Laplace of x, that's capital X. And then we have plus 4, and then parenthesis, Laplace of y double prime is s squared y, all right, s squared capital Y, minus s y of 0, so minus s minus y prime of 0, so minus y prime of 0, minus 4 makes plus 4. All right, now, as before, we're going to rewrite this. So we're going to gather. Here we have 2 x terms and just a single y term. All right, so when we gather, what do we get? Well, for the x, we'll get, don't forget to distribute, 2s minus 3. So 2s minus 3x. And what about for the y? Well, there's just a single y term. So plus 4s squared y equals. Okay, now on the other side, well, for the s, don't forget to distribute. The minus 4s will move across as a plus 4s. All right, that's good. What else do we have? What about our constants? Well, here you have a minus 4. Here you have a plus 16. 16 minus 4 is 12. It goes across. So that becomes a minus 12. All right. Good. 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 Whew. Now, what do you see? Two equations, two unknowns. So we solve. And there's a couple ways we can solve, but we're going to channel our Cramer's rule. All right, so now we're going to switch and Cramer's rule. It's a nice way to solve two equations, two unknowns. Essentially, this is just a fancy way of saying elimination, elimination. We like elimination. Okay, so writing this in matrix form, we would have s squared, 3s minus 2, 2s minus 3, 4s squared, x, y, equal to 2s, 4s minus 12. And Cramer's rule says what? If you're trying to solve for x, which we are, right? We're after x. So we're after x. You do the following. So we have, and I'm going to switch it up because we're near the end. Capital X is the ratio of two determinants. Now the bottom comes from the determinants of the coefficients. S squared, 3s minus 2, 2s minus 3, 4s squared. The numerator, very similar, except the x column gets replaced by these terms. So we have a 2s, 4s minus 12, 3s minus 2, 4s squared. And the rest of this is just taking these determinants and giving ourselves a chance to be patient. So we're going to do our diagonal. So we have 2s, 4s squared, subtract, other diagonal, 4s minus 12, 3s minus 2, divide by diagonal, s squared, 4s squared, subtract, 2s minus 3, 3s minus 2. All right, well, we're going to run out of space, I fear, but be patient with ourselves, right? Give yourself some space. So, what do we have? 2s times 4s squared is 8s cubed. Then we're going to get a 4s times a 3s, so that's 12s squared. A 4s times a minus 2 is a minus 8s, but we're also going to have a minus 36s. That's a lot of minusing going on. But minus 8 minus 36 makes minus 44. Minus 12 times minus 2 makes a plus 24. All right, we'll clean that up in just a second. Downstairs, s squared times 4s squared will give us 4s to the fourth. Subtract. 2s times 3s will be 6s squared. Then we're going to get a minus 4s minus 9s. So that's minus 13s and a plus 6. And if we distribute the minuses through, we end up with 8s cubed minus 12s squared plus 44s minus 24 divide by 4s to the fourth minus 6s squared plus 13s minus 6. And scene. We're done. Right? Because we just had to find capital X of S. And so there you go. So systems work with Laplace transforms. They're really cool and useful tools. And so it's good for us to get comfortable using them. Well, thank you for being so patient and hanging in there all the way to the end. Practice. Become familiar with your rules. The big thing is know when to use which rules and be comfortable, especially going forward because we're going to start doing a lot more mixing of rules. And so it's just a matter of think about them as onion problems. Onions have layers. Work through your layers, and there may be a few tears involved, but hopefully they are tears of joy. Thanks again. Keep working hard. I believe in you. And I hope I get to see you again. Bye.